Hello and welcome to Controllers Tech. This is the 8th video in the STM32 USB series. In the previous videos of this series, we worked with the STM32 USB in device mode. We have covered different USB classes such as CDC, HID, MSC, and even the composite class. From this video onwards, we will start configuring the STM32 USB in host mode, and today we will see how to use the mass storage class in host mode. Here is what we are going to do. I am going to connect a USB flash drive to the STM32 USB port. The STM32 will act as a USB host and will read a configuration file stored on that flash drive. This configuration file will contain two things: the baud rate for the UART, and the delay timing for the LED blinking. The STM32 will read this file and configure the UART and the LED blinking delay based on the values provided in it. This is going to be a fairly long video, because we need to understand the USB host configuration across different STM32 development boards, specifically, which pins are required and how they differ across different boards. I am also going to implement FreeRTOS with the USB peripheral. We will cover one thing at a time, so that we can avoid errors later. Alright, let's start by looking at the USB host configuration available on different STM32 development boards. I am going to use the Nucleo L496 for this USB host series, and the reason for choosing this board is that it provides direct USB host access without any hardware modifications. Let me open the schematic of this board and go to the USB section. If you look here, you will see a pin called PG6, which is the USB power switch on pin. It is connected to the enable pin of the USB power switch IC. In order to activate the USB host, we need to pull PG6 high. If we do not do this, the USB host will not be enabled, and the connected USB device will not receive power or be detected. The next pin we need to take care of is the VBus pin, which is connected to PA9. Most USB devices, such as flash drives, do not have their own power source. It is the responsibility of the USB host to supply power to the connected device, and this is done through the VBus line. The VBus pin, connected to PA9, is used by the STM32 to monitor the VBus line. The actual power to the connected USB device is supplied through the USB power switch, which is controlled by the enable pin we discussed earlier. Other than these two pins, we also have the standard D+ and D- data lines, just like we used in the USB device mode. Now let me also show you the same configuration on a couple of other popular development boards, so you have a clear picture of how this differs. Here I have the schematic of the STM32 F407 Discovery, which is a very widely used board. If you look at the USB section, you will see it also has a power switch on pin, which is connected to PC0. However, note that this time the enable pin is active low, which is the opposite of what we saw on the Nucleo L496. So in order to enable the USB host on this board, we need to pull PC0 low. It should be configured as an output pin, and driven to ground. Only then will the USB host be active. The VBus pin on this board is also connected to PA9, so that part remains the same. Now here I have the schematic of the Nucleo H755ZI. This board also has a USB FS power enable pin, which is PD10, and it is also connected to an active low enable pin. So to enable USB host on this board, we need to pull PD10 low. The VBus pin here is again connected to PA9. Now, I have been using the F446 from the UART Studio throughout the device mode series, but I did not use it for the host series. The reason is that this board does not have a proper USB host configuration by default. If you look at its schematic, you will notice two things. First, there is no dedicated pin available to enable the power for the USB host mode. Second, the V-bus pin is not connected to PA9 in the default configuration. If you look more carefully, you will see that the V-bus pin is connected to VCC through a component labeled SB3. In the schematic, this is shown as a resistor, but on the actual board, this resistor is not populated, the connection is left open by default. If you want to try using this board for the USB host, you could solder a connection at the SB3 position, which would connect V-bus to VCC. However, since this board also lacks a dedicated USB host enable pin, it is not straightforward to use it in host mode, and I am not entirely sure whether this would be sufficient to make it work properly. This is why I decided to go with the Nucleo L496 instead, which has proper USB host support out of the box. Alright, now that we have a clear understanding of how to enable USB host mode on different development boards, let us open STM32CubeMX and create a new project. I am using Nucleo L496, hence I am going to select it from the board selection section. First, let me clear the default pinout. Now we will move to the clock configuration. I will use the internal high-speed oscillator as the clock source, and we will use the PLL to run the system at the maximum possible clock speed of 80 MHz for this board. Go back to System Core, Sys, and enable Serial Wire Debug. Now we will start with the USB configuration. Go to the connectivity section and enable USB OTG in host-only mode. You can see that pins PA11 and PA12 are automatically configured as the USB data pins, just like they were in the device mode. Next, we will enable V-bus sensing. Once enabled, the pin PA9 will automatically be configured as the V-bus sensing pin. What V-bus sensing does is, it monitors the voltage on the V-bus line. If the connected USB device does not have its own power source, the STM32 will enable the power supply for it. If the device already has its own power source, it will not supply any additional voltage. So it essentially monitors and manages the power supply for the connected USB device automatically. Now we will also configure the UART for serial logging, so that we can view logs on the serial console. I am going to use low-power UART 1 for this purpose. The reason is that on Nucleo boards, the virtual COM port is available through the SD-Link, and the low-power UART 1 TX and RX pins are the ones connected to the SD-Link on this board. Let us now configure the UART parameters. Set the baud rate to 115200, word length to 8 bits, parity to none, and stop bits to 1. One thing to note here is that the baud rate for low-power UART 1 can be configured between 9766 bits per second, and 13 megabits per second. This means the very commonly used baud rate of 9600 cannot be used with this particular UART. Now, by default, CubeMX configures PC0 and PC1 as the UART pins. However, if we look at the Nucleo L496 schematic, the SD-Link TX and RX pins are actually connected to PG7 and PG8. So if we want to use the virtual COM port through the SD-Link, we need to reassign the UART pins to PG7 and PG8. Let me do that now. Alright, the UART configuration is complete. Now go to middleware and select USB host. Here we will enable the mass storage class for today's tutorial. We can leave all the parameter configurations at their default values. However, you will notice a warning in the platform settings. This warning appears because the V-bus pin has not been configured in the platform settings section of the USB host middleware. The reason for this is that we have already assigned PA9 for V-bus sensing, so it cannot be used to drive V-bus manually from the middleware settings. On some newer microcontrollers, there is an option to disable this platform setting entirely, since V-bus is already being handled through V-bus sensing. However, this particular microcontroller does not provide that option, so we will simply leave it as it is. The warning can be ignored in our case. Just to note, if you are not using V-bus sensing on your board, You can configure PA9 as a GPIO output pin and then assign it in the platform settings, so the USB host middleware can use it to control VBus manually. But since we are using VBus sensing here, we do not need to worry about that. Now, there is one more thing we still need to configure, the power switch on pin. As we saw in the schematic earlier, pin PG6 is connected to the enable pin of the USB power switch IC. We need to set PG6 as a GPIO output pin, and in the GPIO settings, we will set its default output level to high. This will enable the USB power switch physically, allowing the host to supply power to the connected USB device. That is all the pin and peripheral configuration we need. Now let us go to the clock configuration tab. You will notice an error here. The USB peripheral is receiving a 64 MHz clock, but it requires exactly 48 MHz to operate correctly. We can fix this either by adjusting the PLL multipliers and dividers to output 48 MHz to the USB peripheral, or on this board, we can use the dedicated 48 MHz high-speed internal oscillator, which is provided specifically for this purpose. Now go to the Project Manager tab. Provide a name for the project, make sure the toolchain is set to STM32CubeIDE, and click Generate. CubeMX will show a warning about the platform settings not being fully configured, but as I mentioned, we are already handling VBus through VBus sensing on PA9, so we can safely ignore this warning and proceed to generate the project. Alright, the project has been generated. Let us now import it into STM32CubeIDE. The project has been imported, and here you can see the main file. Now, let's take a look at the main function. CubeMX has generated a function called MX USB Host init, which initializes the USB host. Then inside the infinite loop, the function MX USB Host process is continuously called. This function keeps monitoring the USB host state. I want to make this clear, if CubeMX does not automatically generate this function inside the infinite loop for you, you must add it manually. I noticed this while testing on the Nucleo H755Z, where this function was not placed inside the infinite loop, by default, and I had to add it manually. Without this function being called continuously in the loop, the USB device will never be detected. If you look at how this function is defined, you will find it inside the USB host.c file, which is located in the USB host application folder. This function internally calls USB host process, which will eventually call USB host user process. This is the function where we will write our own code based on the current state of the USB host. There are 4 different states that we need to handle in USB host user process. Let me go through each one. The first state is user select configuration. This state is triggered when the USB host is in the process of selecting a configuration for the connected device. This is an internal state handled by the USB host stack and typically does not require any action from us. The second state is user disconnection. This state is triggered when the USB device is disconnected from the host. The third state is user active class. This state is triggered when the USB device has been successfully connected and is ready to use. The fourth state is user connection. This state is triggered when a USB device is connected for the first time and the host begins the enumeration process. Before we start working with the actual files on the USB flash drive, we should first verify that these states are being triggered correctly. So I am going to add some simple log messages inside each state, so we can confirm the behavior on the serial console. Now, in order for printf to route its output through the UART, we need to define a custom write function. I will define it in the main file and route the output through low power UART1, which is the one we configured in CubeMX and which is connected to the ST-Link virtual COM port. Alright, let's build the project. There are no errors, so let's flash it to the board. Now open the serial monitor. we need to connect to the STM32 virtual COM port. Make sure the settings match what we configured in CubeMX, baud rate 115200, 8 data bits, no parity, and 1 stop bit. At this point, the USB device is not yet connected. Before I plug it in, let me show you something about the flash drive I am using. I connected it to the computer, and you can see it appears in the File Explorer. If we check its properties, it is a 16 GB flash drive formatted with the FAT32 file system. This is important, the flash drive must be formatted as FAT32, otherwise the STM32 USB host will not be able to read it. Now, before I plug the flash drive into the STM32, notice that there is a small LED on the board that is already turned on. This LED indicates that the USB port is active and power is being supplied through the V-bus line. This LED will only turn on if the power switch on pin, PG6 in our case, has been configured and set high. If that pin is not configured, this LED will remain off and the USB port will not supply any power to the connected device. Alright, let's now plug the flash drive into the STM32 USB port. You can see on the serial console that the application has started, and the connection and active class states have been triggered successfully. This confirms that the USB host is working correctly, and the device has been detected. We can now proceed with the actual USB implementation. Let's go back to STM32CubeMX, go to middleware, and enable FatFs for the USB disk. Since we are using a USB device as our storage medium, we need to select the USB disk option. We do not need to change any other configuration here, but make sure that the device is not set to read-only mode, otherwise we will not be able to write to the USB device later. Now let's generate the project again. Alright, the project has been generated. Let us go back to STM32CubeIDE. In the USB Host.c file, include the ff.h header file, which is the main FatFs header. Now, the FatFs library files are stored in a separate folder in the project. Inside it, you will find the FatFs.c file. This file already defines the USB path variable, and the file system object variable. We need to use these same variables in our USB Host.c file, so we will declare them as external variables there. This way we are not redefining them, we are simply referencing the definitions that already exist in FatFs.c. Let us also define an fresult variable to store the return values of the FatFs functions. We will use this to check whether each operation succeeds or fails. Now we will first test the mounting and unmounting of the USB flash drive to confirm that FatFs is working correctly. Inside the user active class state, we will call the fmount function to mount the USB drive. This function takes 3 arguments, the file system object, the path, and a mount option. The file system object and the path are the ones we declared as external variables. For the mount option, we will pass 0, which means the file system will be mounted lazily, it will not mount immediately, but will do so when the first file operation is performed. If the mounting is successful, this function returns FROK, and in that case we will print a success message on the serial console. Otherwise, we will print a failure message. Similarly, inside the user disconnection state, we will call fmount again, but this time with a null pointer for the file system object, which tells FatFs to unmount the drive. If this is successful, we will print a log message confirming that the drive has been unmounted. Alright, let us build the project. There are a few errors, but they are due to a mistake I made in the function names. Let me fix those quickly. Alright, all the errors are fixed. Let us flash the project to the board and open the serial console to view the logs. Now I am going to connect the USB flash drive. You can see on the console that the mount was successful, the STM32 USB host was able to mount the USB device. When I disconnect the device, you can see that the drive is unmounted as well. And when I plug it back in, it mounts again automatically. So this is essentially a plug-and-play setup. You do not need to reset the board every time you plug or unplug the USB drive. The mounting and unmounting happen automatically based on the connection state. Everything is working correctly so far. Now, as I mentioned earlier, I am also going to implement a real-time operating system for this project. In my previous USB series videos, many of you had issues with FreeRTOS implementation, so I am going to set it up here from the beginning so that everything is in place. Let's go back to CubeMX, then in the middleware section, go to FreeRTOS and enable the CMSys version 2 interface. You can leave most of the settings at their default values, but there is one important thing to take care of, the heap size. Make sure you provide a sufficiently large heap size. The USB host process alone can consume around 4 kilobytes of heap, and in some cases even that is not enough. Depending on your application, you may need 8 kilobytes or more just for the USB processing. So I would recommend providing at least 20 to 30 kilobytes of FreeRTOS heap space to be safe. Now let's go to the tasks and queues section. The default task is already created, and it will be by default used for initializing the USB peripheral. A stack size of 128 words is sufficient for this task. I am now going to create 2 additional tasks. The first one is for printing logs on the serial console. I am calling it UART task, and its priority will be set to normal. Make sure to provide at least 512 words of stack size for this task, because it will be calling printf frequently, and printf requires a significant amount of stack memory. The second task is for blinking the LED. I am calling it LED task, and its priority will also be set to normal. A stack size of 128 words is sufficient for this task. Alright, that is all we need to configure in FreeRTOS. If you check the heap usage summary, you can see that around 16 kilobytes of heap is still available, so we have plenty of room. Now go to Advanced Settings and make sure to enable the new library entrant feature. This is necessary because we are using printf across multiple tasks, and enabling this feature ensures that the standard library functions work correctly in a multi-threaded environment. Now, looking at the Nucleo L496 schematic, the pin PB7 is connected to the blue LED on the board. So let's configure PB7 as GPIO output pin so that the LED task can control it. Now go to the USB host configuration. You will notice that RTOS support is already enabled by default when FreeRTOS is active. The USB host middleware creates its own internal task for processing. The priority of this task is set to normal, and we will leave it at that. If you find that other tasks are preempting it and causing issues, you can increase its priority. But since all our tasks are at normal priority, it should not be a problem. Now, the stack size for the USB host processing task is set to 128 words by default, which is not enough, especially since we are also calling printf functions inside the USB host callback. I would recommend setting this to at least 1024 words, which gives it 4 kilobytes of stack space. One thing to note here, when I was testing this on the Nucleo H755, CubeMX did not allow me to change this stack size. It was set to 0 by default and kept resetting back to 0 even after changing it. If you face the same issue, you can leave it at 0, but in that case make sure your FreeRTOS heap is large enough, because the stack memory will then be allocated dynamically from the heap at runtime. If your USB processing task gets stuck or crashes midway, the first thing you should do is increase this stack size. Alright, there is one more thing to configure before we generate the project. Since we are using FreeRTOS, we should use a dedicated timer as the time-based source for the HAL library instead of systic, because FreeRTOS itself uses systic for its own scheduling. I am going to configure timer 6 as the whole time base source. Alright, that is all the configuration we need. Let us regenerate the project. The project has been generated. Let us go back to STM32CubeIDE and open the main file. If you scroll down to the bottom, you will see that the default task is responsible for initializing the USB host by calling MX USB host init. You will also notice that we have the UART task and the LED task listed here, but you will not find the USB host process function being called anywhere in the main file. This is because when FreeRTOS is enabled, the USB host library handles the processing internally through its own dedicated task, which is why we configured the USB host task stack size separately in CubeMX. So we do not need to worry about calling it manually. Now, inside the UART task, I am going to print the string every 1 second. And inside the LED task, I am going to toggle pin PB7 every 1 second. Now let us open the USB host.c file. As I mentioned, the MX USB host process function is no longer visible to us directly when using FreeRTOS, but regardless of how it is being called internally, the USB host user process callback will still be triggered in the same way. So we still write our USB state handling code inside this function, and the code we wrote earlier is still intact here. Let us build the project. There are no errors, so flash it to the board and verify that everything is working correctly. You can see on the serial console that after the USB is mounted, the hello world string is printing every 1 second. The blue LED on the Nucleo board is also blinking every second. The USB device is mounting and unmounting successfully without any issues. Alright, so our FreeRTOS tasks are working correctly, the USB host is functioning as expected, and everything is stable. We can now proceed further with the actual file reading implementation. As I mentioned at the beginning, I am going to create a configuration file on the USB flash drive. So let me create a new text file. Inside this file, I will provide two values, the baud rate, and the LED delay. I am setting the baud rate to 14,400, and the LED delay to 250, which will be 250 milliseconds. Let us save this file and name it config.txt. Now let us copy this file to the root of the USB flash drive, and go back to STM32CubeIDE to write the file reading code. After the drive is mounted successfully, we need to open and read the configuration file. So I am declaring a file object variable called myFile, and I am also creating a buffer where we will store the content read from the file. Now, after the mount is successful, we will call fopen to open the file. We pass the file object myFile, the file name config.txt, since the file is in the root of the drive, we only need to provide the file name without any path, and the mode for read, since we only want to read this file. If the file is opened successfully, this function will return FROK, and in that case we will proceed to read the file. Otherwise, we will print an error message indicating that the file could not be opened. To read the file, we will call fread. This function takes 4 parameters, the file object, the buffer where the data will be stored, the number of bytes to read, and a pointer to a variable where the actual number of bytes read will be stored. For the number of bytes to read, we pass size of the buffer, which is the maximum number of bytes we want to read, not the size of the file itself. We reserve 1 byte at the end for the null terminator. We also need to declare the bytes read variable, and pass its address to the function. If fread returns success, we will process the data. Otherwise, we will print an error message indicating that the file could not be read. Before printing the buffer contents, we will first store a null character at the end position of the buffer. This marks the end of the data we read, and ensures the buffer is properly null terminated before we use it as a string. Then we will call printf to print the buffer contents on the serial console, so we can verify that the file is being read correctly. Also, it is important to close the file after we are done with it. So after the read operation, we will call fclose to close the file object. This should always be done after you are finished reading or writing a file. Alright, let us build the project. There are no errors, so flash it to the board. Right now the USB device is not connected. Let me plug it in now. You can see on the serial console that the mount was successful, and the file contents are printed exactly as we stored them on the flash drive. So the STM32 is able to open and read the configuration file correctly. Now we will actually parse the data from the file and use it to configure the UART baud rate and the LED blinking delay. Let us start by defining the necessary variables inside the main file. I am going to define 3 variables, one to store the baud rate received from the configuration file, one to store the LED blink delay, and one flag variable to indicate whether the baud rate has been changed. This flag will be used by the UART task to detect a baud rate change and apply it. Now we will declare these same variables as external variables inside USB Host.c, so that we can access and update them from within the USB user process function. Alright, after the file content has been successfully read into the buffer, we now need to parse it and extract the key value pairs. I am defining 2 character arrays, one to store the key, such as baud rate or LED delay, and one to store the corresponding value. Now, to parse the file content line by line, we will call the string tokenizer function on the buffer, using carriage return and new line characters as delimiters. This will give us one line at a time. We will process each line inside a while loop. For each line, we will call the scanf function to extract the key and the value. Let me explain how the format string works here. It begins with a space, which tells the function to skip any leading white space. Then we specify that it should scan up to 31 characters and stop when it encounters a colon. This extracts the key, for example, baud rate, and stores it in the key array. After that, the colon itself is consumed. Then a space is included to skip the space that comes after the colon. Next, we specify a quotation mark, because in our configuration file the values are enclosed in quotation marks. Then we again tell it to scan up to 31 characters, and stop when it hits the closing quotation mark. This extracts the actual value, for example, 14,400, and stores it in the value array. Finally, the closing quotation mark is consumed. The scanf function returns the number of items it successfully extracted. Since we are extracting 2 items, the key and the value, it should return the number 2 if the extraction was successful. We check for this before proceeding further. Once we have the key and the value, we use the string compare function to compare the key against the expected strings from our configuration file. If the key matches baud rate, we convert the value from a string to a number using the a_to_i function, and store it in the baud rate variable. We also set the baud change flag to 1, so the UART task knows that a new baud rate needs to be applied. A confirmation log is then printed on the serial console. Similarly, if the key matches LED delay, we again use the a_to_i function to convert the value and store it in the LED delay variable, followed by a confirmation log. Now, we have only extracted 1 line so far, but our configuration file has multiple lines. So we call the string tokenizer function again, this time passing null as the first argument, which tells it to continue from where it left off and move to the next line. This keeps repeating inside the while loop until all lines in the file have been processed. That is all we need to do inside the USB host source file. Now let us go back to the main file and handle the configuration changes in the respective tasks. Inside the UART task, we will check if the baud change flag is set to 1. If it is, we need to apply the new baud rate. We cannot simply change the baud rate on the fly, we need to first initialize the UART using UART init, Then update the baud rate field in the UART handle with the new value, and then reinitialize it using UART init. After applying the change, we reset the baud change flag back to 0, so this does not execute again on every iteration of the task. We also print a message on the console asking the user to update the baud rate on their serial monitor, otherwise the logs will no longer be visible after the change. Inside the LED task, instead of the fixed 1-second delay we had earlier, we will now pass the LED delay variable, so that the blinking rate is controlled by the value read from the configuration file. I want to mention one important thing. The baud rate variable, and the LED delay variable must be initialized with default values. This is necessary because the LED task and UART task start running immediately when the baud powers on, even before the USB drive is connected and the configuration file is read. If the FreeRTOS delay in the LED task is 0, it will cause the task to run continuously without yielding, and will cause the scheduler to behave incorrectly. I am initializing the baud rate with 11.5200 and the LED delay with 1000 milliseconds. Alright, that is all the changes we need. Let us build the project. There are no errors, so flash it to the board. Now, open the serial console. Initially, you can see the UART is printing normally at 11.5200 baud rate, and the LED on the board is blinking every 1 second. Now I am going to connect the USB flash drive. As soon as it is connected, you can see a log message on the console asking us to change the baud rate to 14,400. Let us do that. As soon as the baud rate is changed on the serial monitor, the data starts printing again. The LED is also now blinking every 250 milliseconds, which confirms that the LED delay was also applied successfully from the configuration file. Now, even if we disconnect the USB drive, the data continues to print correctly, because the UART is now configured at 14,400, and will remain at that rate until it is changed again. When we reconnect the USB drive, we do not need to change the baud rate on the console again since it is already set correctly. Let's now test this with different values. I am going to modify the configuration file. I am setting a higher baud rate, and a shorter LED delay this time. Save this file, copy it back to the USB drive, and connect it to the STM32. You can see the log is now asking us to switch the baud rate to 230,400. Let's change it on the serial monitor, and you can see the data starts printing again. Also notice that the LED is now blinking significantly faster at 100 milliseconds. So the STM32 can successfully read the configuration data from the USB device, and applying it to its peripherals. Now let me quickly demonstrate how we can also write data to the USB device. This will be a brief example. After the configuration file has been opened, read, and closed, I am going to call the function fopen again. This time I will provide a file name test.txt, which does not exist on the USB drive yet. I will pass the mode create always, combined with mode write. Which means it will create the file if it does not exist, or overwrite it if it does, and open it for writing. If the file is created and opened successfully, we will call fwrite to write some data to it. I am writing a short string, and the number of bytes to write is set to 20. We also need to define a bytes written variable and pass its address to fwrite. This variable will hold the actual number of bytes written to the file, which should match the number we requested. If it does, the write was successful. We will print this value on the console for confirmation. After the write is done, we close the file using fclose. Also, I am going to comment out the baud rate change part for now, so that we do not miss the write-related logs on the console due to a baud rate switch. Let's build and flash the project. We will also need to switch the baud rate on the serial monitor back to 115,000, 200 since the board is restarting. You can see from the logs that 20 bytes were written to test.txt. Let me disconnect the USB drive and connect it directly to the computer. You can see a file called test.txt has appeared on the drive, and it contains exactly the data we wrote using FWrite. So our read and write operations to the USB device are both working successfully. We saw how to configure the STM32 as a USB host, how to use the mass storage class to read and write data to a USB device, and how to use a configuration file stored on a USB flash drive to configure peripherals on the STM32 at runtime. That is it for this video. In the next video, we will look at the HID class, and we will start by configuring the STM32 to read data from a mouse. You can download this project from the article linked in the description below. If you have any questions or suggestions, feel free to leave them in the comments. Keep watching, and have a nice day.